Hey you guys, this is Mr. Millings, and in this video we are going to learn about something called colligative properties. And before we watch this video on colligative properties and go over this information, here's a little disclaimer for you. It says that prior knowledge of the topics listed below is essential before watching this video. So I recommend that you watch the video on how to calculate the molality of a solution, and you watch the video on solubility explained before watching this video. So what are colligative properties and how do they work? Well, let's take a look. It says right here that colligative properties are properties of a solution, example boiling point, freezing point, vapor pressure, and osmotic pressure, that depend on the amount of dissolved solute particles in the solution and do not depend on the type of chemical species present. So essentially, colligative properties are properties of a solution that deal with the boiling point, freezing point, and vapor pressure, as well as osmotic pressure of a solution when we start dissolving particles in that solution. So for example, if we take a look over here, we have a mound of sodium chloride or table salt. And if we take a look at what table salt might look like on a microscopic level, it looks like we see right here. It forms this crystal structure that we see right here. And so if we take a look, we have a bunch of chloride ions which are negative, tightly packed in with some sodium ions which have a positive charge. And we learned that in an earlier video, when you put this in water here, it's going to dissociate, it's going to dissolve and dissociate. It's going to break apart into chloride ions that are floating around in this water and sodium ions that are floating around in this water. So what ends up happening is that anytime you have particles like this that are floating around in water, it's going to increase the boiling point of that solution, and it's going to decrease the freezing point of that solution. So when we add an ionic compound like salt or sodium chloride to water, it's going to dissociate and produce some ions that are free floating in this water right here, and that's going to cause it to have its boiling point increased and its freezing point decreased. And the same thing with sugar. If we take some sugar here and we put sugar in water, we know from prior experience that it too is going to dissolve, right? And so we can take a look right here, and yes, sugar is going to dissolve, but it's not going to dissociate. It's not going to break apart like we see this ionic compound do on the left-hand side. And so if we take a look right here, this sugar is going to dissolve in water, and so its freezing point, the freezing point of this solution is going to decrease, and the boiling point of this solution is going to increase as well. So in both scenarios here, the boiling point of the solution is going to increase, the freezing point of the solution here is going to decrease. And same right here, the boiling point of this solution is going to increase and the freezing point is going to decrease. But if I were to ask you which one of these will have a higher boiling point now and a lower freezing point, which one would it be and why? Well, that's what we're going to talk about in this video. If we take a look over here, when we put sodium chloride in water, it's going to dissociate. And so if we have 1 mole of sodium chloride, it's going to produce 2 moles of particles. It's going to produce 1 mole of sodium ions and 1 mole of chloride ions for a total of 2 moles. And so because there's more dissolved particles in this solution here, the boiling point elevation is going to be greater and the freezing point depression is going to be greater. If we compare this to just sugar, if we take a look at sugar, if I have 1 mole of sugar, it's not going to dissociate, so it's going to produce or there's only going to be 1 mole of sugar particles that are floating around in this beaker of water here. So that is why sodium chloride dissolved in water is going to give a higher boiling point and a lower freezing point compared to sugar dissolved in water. So let's take a look at a couple more examples of this phenomenon and compare and contrast the differences between them. And so it says right here that ionic compounds will typically increase the boiling point and decrease the freezing point more than polar molecules if equal amounts are dissolved. This is because ionic compounds dissociate in water and produce more dissolved particles than equal amounts of polar molecules. So right here, once again, we have some sugar, and when we put 1 mole of sugar in here, it's going to produce 1 mole of dissolved particles in this solution because it does not dissociate, it does not break apart. If we take a look right here, if we take this 1 mole of sodium chloride and we put it in here, it's going to dissociate and produce 1 mole of sodium ions and 1 mole of chloride ions for a total of 2 moles of dissolved particles. And if we take a look at this substance here, K2S or potassium sulfide, if we dissolve 1 mole of this in this solution right here, or in this beaker of water right here, it's going to dissociate too, because it's an ionic compound, and it's going to end up producing 1 mole of sulfide ions and 2 moles of potassium ions, for a total of 3 moles of dissolved particles that are floating around in this solution. So if we asked which of these 3 solutes will cause a higher boiling point elevation and a lower freezing point depression, it's going to be this one right here. It's going to be this one right here, because there's going to be 3 moles of dissolved particles in here, only 2 moles of dissolved particles in here, and only 1 mole of dissolved particles in here. So what we can do is we can actually use a formula to calculate the boiling point elevation and freezing point depressions of different aqueous solutions that have different types of solutes dissolved in them. So let's take a look at that right now. And so it says right here that when particles dissolve in water, the boiling point of the solution increases. And it says that this is known as boiling point elevation and can be calculated using the formula below. So we have the formula right here, that the change in temperature of the boiling point, in this case of water, if we're talking about that as the universal solvent, is going to equal this right here, Kb, which is the boiling point constant of water, which is always equal to this right here, 0.512 degrees Celsius kilograms per mole, multiplied by the molality of the solution, multiplied by I. What is I here? This is known as the Van 't Hoff factor. And what this is this represents the number of particles that the substance or solute will dissociate into. And for polar molecules, this is always going to be a 1, since it doesn't dissociate. So let's take a look now at the freezing point depression formula and how we can use that to solve problems with dissolved particles in a solution. And so it says right here that when particles dissolve in water, the freezing point of the solution decreases. And this is known as the freezing point depression and can be calculated using the formula below. So the formula that we just looked at looks very similar to this, except it's for the boiling point elevation of different solutions. And this here is how we are going to calculate the freezing point depression of different solutions. And so if we take a look right here, to get the change in the freezing point temperature in degrees Celsius, we simply take the freezing point constant of water, if we're talking about water as our solvent, and that is going to be equal to 1.86 degrees Celsius kilograms per mole, times the molality of the solution, times the Van 't Hoff factor again. And so what we're going to do now is we're going to apply these 2 formulas to 4 different problems, and hopefully you catch on. In this first example, it says to calculate the boiling point of a 2.5 molal aqueous solution of sodium chloride. And we're going to assume we're at sea level. And so we know that the boiling point of water at sea level is going to be equal to 100 degrees Celsius. So we know its boiling point at sea level is 100 degrees Celsius. And what we're going to do is we're going to add salt to this water here, and so there's going to be a boiling point elevation. And so how do we calculate the boiling point elevation? Well, to get the change in the boiling point, we take the boiling point constant times the molality times this I here, which is known as the Van 't Hoff factor, and this here is essentially the number of particles that this will dissociate into when we put it in solution. And so if we take a look here, let's go ahead and set this up. To get the change in the boiling point of our solution now, we're going to take the boiling point constant times the molality of the solution times this thing called the Van 't Hoff factor. And so right here, Kb, that is the boiling point constant of water. And this is different for every substance or every solvent. And if we take a look, the boiling point constant of water is going to be 0.512 degrees Celsius kilograms per mole. And so we just talked about this when we talked about the boiling point elevation formula a couple of minutes ago. So this is a constant. This is always the same for water. So we'll go ahead and plug that in here. 0.512 degrees Celsius times kilograms per mole times the molality of our solution. This little m here stands for the molality of the solution, and that is usually, or that is always measured when we're talking about molality in moles per kilogram. And then we're going to multiply this by the Van Hoff factor. And so let's think about this. If I have a beaker, if we have a beaker of water here, and we put this into water, if we take sodium chloride and we put it in water, we know from an earlier video that this is going to dissociate. It's going to break apart into two different types of ions floating around in here, sodium ions and chloride ions. So this is going to break apart and dissociate into two different types of particles. So our Van Hoff factor here is 2. And so now we just get a calculator out, and we're going to take 0.512 times 2.5 times 2. And we're going to end up with 2.56. 2.56 degrees Celsius. If you take a look, kilograms is going to cancel out, moles is going to cancel out, leaving us with degrees Celsius. However, this is just the change in the temperature. This is just delta T. What we now have to do to get the boiling point is we have to take this and add this to our boiling point at sea level. And so we know that the boiling point of water is normally 100 degrees Celsius at sea level, but we're going to add 2.56 since there's an elevation in the boiling point. And when we put this in our calculator, we should end up with 102.6. We'll just call it 102.6 if we're rounding to the 10th place degrees Celsius. So when we add this salt to water, it's going to raise its boiling point to 102.6 degrees Celsius. Let's take a look at another example. In this example right here, it says to calculate the freezing point of sugar water solution that is made by dissolving 250 grams of sugar, C12H22O11, in 3,575 milliliters of water. And we're going to assume that we're at sea level again, so the pressure doesn't come into play. And so if we take a look here, we're dealing with sugar water solution. And so we're asked to calculate the freezing point. And so normally we know that the freezing point of water is 0 degrees Celsius at sea level. And so what we're asked to figure out is the change in the freezing point. And so to get the change in the freezing point, we have to take the freezing point constant of water times the molality of our sugar water times the Van Hoff factor. And so if we take a look here, let's go ahead and solve this problem. We know from a couple of minutes ago when we talked about this formula right here that the freezing point constant of water is equal to 1.86 degrees Celsius times kilograms per mole. So we're going to plug that in here, 1.86, right? Degrees Celsius times kilograms per mole times the molality of our solution. And so molality, what is molality? Well, molality is equal to moles of solute over kilograms of solution. And so if we take a look here, what we have to do is we have to convert this to moles, right? We have to convert this stuff right here to moles. So we have to figure out the molar mass of this. So let's go ahead and do that right here. The molar mass of C12H22 O11 from our periodic table, we know that there's 12 carbons times 12.01 grams per mole for our carbons. We're getting this number from our periodic table of elements. If we take a look here at hydrogen, there's 22 of them. And we're going to multiply this by the molar mass of hydrogen, which is 1.01 grams per mole. And then we take a look at oxygen, and there's 11 of them. So we're going to take 11 times 16 grams per mole, which is our molar mass of oxygen. And so when we put this all in our calculator, we will end up with our molar mass of sugar. So let's go ahead and do that. We get a molar mass of 342.34 grams per mole. So that is just our molar mass, right? That is just our molar mass. It says that we have 255 grams of sugar. So we have to figure out how many moles of sugar this is. And so let's go ahead and do that. If we have 255 grams of C12 H22O11, and we want to convert this to moles, we know that 1 mole of C12H22O11 is going to be 342.34 grams. So we'll put this in our calculator. We'll take 255 divided by 342.34, and we're going to end up with 0.745, it looks like. 0.745 grams. I'm sorry, moles, I apologize, moles. So, to get our molality, we're simply going to take 0.745 moles, and we need to divide it by the kilograms of our solvent. So how do we get that? Well, this is 3,575 milliliters. We know the density of water is 1 gram per milliliter. So this is 3,575 grams of water. And if we slide the decimal to the left, we'll end up with kilograms. So we have 3.575 kilograms. And so when we put this in our calculator, when we take 0.745 and divide this by 3.575, we're going to end up with 0.208. We'll put this up here. 0.208 as our molality. And so this is not our final answer. We're just going to plug this right into here now. So our molality we just found out was 0.208 moles per kilogram. And if we take a look, we're dealing with sugar. Sugar is not an ionic compound. We can tell it's not because we have all nonmetals here. So this is a molecule, right? This is a covalent molecule. And this is a polar covalent molecule because of the hydrogen-oxygen bonds in this sugar molecule. And so if we take a look here, this is not going to dissociate. It's not going to break apart. And so if we dissolve 1 mole in the solution, it will produce 1 mole of particles. So our Van Hoff factor here is just 1. So we'll put this in our calculator now. We'll take 1.86 times 0.208 times 1. And we're going to end up with 0.387 degrees Celsius. This will cancel out with this. This cancels out with this, leaving us with degrees Celsius. But this is just our change in the freezing point. We know normally that the freezing point of water is 0 degrees Celsius. We now need to subtract the change. We need to subtract the change in our freezing point, which is 0.387. And we will end up with a new freezing point of negative 0.387 degrees Celsius. There we go. So what is the freezing point, or the new freezing point of this solution, going to be? Negative 0.387 degrees Celsius. Let's take a look at another example. In this third example, it says the boiling point of ethanol is 78.4 degrees Celsius. We need to calculate the boiling point constant. So we're trying to find Kb, or the boiling point constant of ethanol, if 2.5 moles of lithium chloride is dissolved in 175 kilograms of ethanol, while its boiling point increases to this right here. We're going to assume that we're at sea level. So there's a lot going on here. First of all, it tells us that the boiling point of ethanol is 78.4 degrees. We're going to dissolve some lithium chloride in it. And so if we dissolve lithium chloride in ethanol, it's going to increase its boiling point. And it looks like it's increased the boiling point to 81.8. And what we're asked to figure out is the boiling point constant. We're asked to figure out the boiling point constant of this ethanol. And so what we could do is we can start to move this formula around. So if we know we'll start over here, that the change in the boiling point temperature is equal to the boiling point constant times the molality of the solution times this Van Hoff factor here, and we're asked to solve for this right here. Then what we can do is divide both sides by the molality and I here. We'll divide both sides by the molality and I here, or the Van Hoff factor, and they're going to cancel from here. And so it looks like to get the boiling point constant of our solvent, in this case ethanol, we take the change in temperature of the boiling point, or the change in the boiling point temperature, and we're going to divide this by the molality times the Van Hoff factor. So that's how we're going to solve this problem. So let's take a look further here. Let's see here. We see, first of all, that the temperature, the boiling point temperature, starts normally at this right here. It's 78.4 and it goes up to the right here. So how do we get the change in temperature? To get the change in the boiling point temperature, we take the final temperature minus the initial temperature. And so our final temperature is 81.8 degrees Celsius. Our initial temperature is 78.4 degrees Celsius. And when we put this in our calculator, when we take 81.8 minus 78.4, we're going to end up with 3.4, it looks like, 3.4. So the change in temperature here is 3.4 degrees Celsius. So we'll put that right here, 3.4 degrees Celsius. And we're going to divide this by the molality of the solution. Now keep in mind that molality is equal to moles of solute over kilograms of solvent. So if we take a look here, what are we dealing with? We have 2.5 moles of lithium dissolved, it says right here, in 1.75 kilograms of ethanol, which is our solvent. So we have 1.75 kilograms. So when we put this in our calculator, 2.5 divided by 1.75, we end up with 1.43 approximately. 1.43 as the molality of our solution. So we'll go ahead and put that right here. We'll substitute that in. 1.43 moles per kilogram. And last, we need to multiply this by the Van Hoff factor. If we take a look, we are dealing with lithium chloride. And if we have a beaker of water here and we put lithium chloride into it, it's only going to dissociate into two different particles, or two different moles of particles. If we add 1 mole of this, we're going to end up with 1 mole of Li plus and 1 mole of Cl minus particles that are in our solution right here. So our Van Hoff factor is going to be 2. So we'll put this in our calculator. We take 3.4 and we're going to divide this by, and if we put in the denominator here, if we multiply these two terms, we need to put them in parentheses in our calculator. 1.43 times 2. And we're going to end up with 1.19 approximately. 1.19 what? Well, if we take a look, our units left over are going to be degrees Celsius. And if we flip this to kilograms per mole, then we multiply by it, not divide by it. So we're going to put times kilograms per mole. So there is our boiling point constant of ethanol. So if you like this video and you like what you see, go ahead and click that little bomb in the bottom right hand corner, and that will subscribe you to my channel. And feel free to leave any comments or questions in the comment section down below. And I really hope you guys found this helpful.